This conference will now be recorded.
Hello guys, again, how are you? So again, we will continue here today, covalent bonding. So in covalent bonding, we talk about allotropes diagram, and today we talk about simple covalent structures. As you remember from the start of our topic, covalent bonding, we wrote that there are two types of covalent structures. They were covalent structures. First, simple covalent structures, and second one was giant covalent structures. So we will talk about simple covalent structures. What are the simple covalent structures? As we said before, the simple covalent structures were made by the help of identical atoms or different atoms of nonmetals. Giant covalent structures we know: diamond, graphite, and silicon peroxide. We'll talk about them in the next lesson, but now we'll talk about simple covalent structures. Okay, so simple covalent structures. Simple covalent structures, as you see from the PowerPoint, most of the constituent covalent molecules have low melting and boiling points, and they are mostly gases or liquids at room temperature. For example, water, oxygen, chlorine, hydrogen, carbon dioxide, and etc. So, what makes them? They have low melting and boiling points, and they are mostly liquids or gas at room temperature. So, this answer lies on force attraction between the molecules. If you remember from in ionic bonding, we said that there is electrostatic force attraction between the positive metal ion and negative non-metal ion. But what about here? So in covalent bonding, we have two types of force attractions here. So, or bonds, let's say. There are weak and strong bonds here. Where are they? So as you see from the PowerPoint, let's say I have a water molecule, H2O, and between oxygen and hydrogen, there is one and totally two bonds. These two bonds are strong bonds or strong force attractions, let's say, strong force attractions, which we showed before that. Again, there is a electrostatic force attraction. By the way, there are repulsion forces between the shared electrons. Okay, electrostatic force attraction because of positive nucleus of each nonmetal. Let's show it again. Positive, and there were shared electrons here. I will show the shared electrons like this. Between positive and negative ions, we'll have electrostatic force attractions. But between two shared electrons, there will be a repulsion force. These are electrostatic force attractions. Static force attractions. So, as I said before that, within the molecule, we call it within the molecule, there are strong force attractions. But if you have another water molecule, let's say HOH, another water molecule, molecules, they will be weak force attractions. So this makes simple covalent structures have low melting and boiling points, weak force attractions. This weak force attraction we call van der Waals forces. You will see in the high levels. So there are two types of force attractions here again. First, what are they? Within the molecules, let me write for you. Within the molecules, there are strong force attractions or strong bonds, but between the molecules, as you see, between two water molecules, there are weak force attractions. So this makes them to have low melting and boiling point. So it's easy to break down these molecules from each other. It's easy to break down these molecules from each other. Okay, so because of that, when you are throwing a harder one solid to the ground or some way, it can easily shatter and break down. But what happens in water molecule? If you are draining the water, water can easily go in one direction, in one pathway. How it happens? Because this weak force attractions, this weak force attraction hold the water molecules with each other strongly, each other, so they can easily go in one direction. Okay, so because of the this type of molecules, I mean simple covalent structure, are at gaseous or liquid state. Okay, also that contain simple covalent molecules, some of them are at solid state at room temperature. So one of them, for example, is iodine, is a non-metal. Other one could be sulfur, for example. So what you observe from iodine's structure, in iodine, as you see here, in iodine, as you see, again between two iodines, there is strong force attraction or strong bonds. As you see, they are written as bold. But weak force attraction are between two iodine molecules. First iodine molecule, second iodine molecule. But between them, as you see, there are just simple dots. These dots represent weak force attractions here. So between the iodine molecules, there are weak force attractions. So solid is formed because the millions of iodine molecules are held together by weak force attractions to create 3D lattice structure. What properties would you expect molecular solids to have with this type of structure? Simply, it's just simple logic. So again, if there are weak force attraction, they will have low melting and boiling point. Usually they are soft and brittle because they are solid, and they cannot conduct electricity. Remember that only non-metal which conducts electricity is an allotrope of carbon, which is graphite. Why it conducts electricity, we will talk about again, because graphite has one free or delocalized electron. So weak force attraction between the molecules can be broken down by small amount of energy. So because of they are solid and have low melting and boiling points. This one you can practice at home if which one is true, which one is false. For example, covalent bonding occurs between non-metals. For example, you will put here, so it's true. So others you can solve by yourself too here. So you can pass now. Giant covalent structures. Giant covalent structures giant covalent structures. What are the giant covalent structures? We have three types of giant covalent structures. These are diamond, which is the most expensive, one of the most expensive materials in the world. Diamond, graphite, and silicon dioxide, or quartz mineral, which is in the sand. Okay, so what we see here, these three structures are giant covalent structures. If you want another name for giant covalent structures, simply you can call them as macromolecules. Macromolecules. Giant covalent structures are macromolecules. Okay, so the covalent bonds in these substances do not form molecules, but vast of networks of atoms called giant covalent structures. So we don't have here molecule, we have a vast of network. Again, you will see, for example, what does vast of network means. You just imagine a spider's web, how the spider web branches into several branches, or the roots of the trees. They are making vast of network structure here. Okay, just simply in the diagram we will show to you. So one carbon joins with four carbons, again this joins with other carbons, four, again it will join with other four, so it will contain millions of carbons will join with each other to make a vast of networks. So they are not making, they do not form molecules, they form a vast of network. So all the bonds are covalent, so giant covalent structures have high melting and boiling points, and they usually are hard. Okay, do not forget it. Please, 3 giant structures we have: diamond, silicon dioxide or sand, let's say simply, and graphite, which is in the pencil beads. So silicon or dioxide or sand is mostly made of mineral quartz. Sand is mostly made of mineral quartz. Okay, among these giant structures, remember the properties of diamond and silicon oxide or silicon dioxide. They have similar properties. How they are similar to each other? For example, you see the structure is shown here. So each silicon here, which has 14 electrons and 2, 8, 4 electrons, is bonded with 4 oxygen, and each oxygen atom is bonded with 2 silicons. But teacher, why we don't have here 2 silicons? Because just simply shortcut of the molecule. If you will take, I will show you now. If you will take this structure from here, for example, you will see that like this. Look at here, the yellow one is silicon. So one silicon is joined with 1, 2, 3, 4 oxygens, but each oxygen is joined with 2 silicons, first, second silicon. This oxygen, first, second silicon. This oxygen, first, second silicon. This oxygen, first and second silicon here. Okay, so because we say that each oxygen is bonded with 2 silicons. So what this makes in about what idea it gives us here. So structure easily explains that here, one silicon joined with 4 oxygens, and each oxygen joins with 2 silicons. I will show you as I showed in the drawing. So if one silicon joined with 4 oxygen, and if one oxygen joined with 2 silicons, if you will just simplify this number, what you will get from here, 2-to-1 ratio. It means your compound, yes, truly will be SiO2, silicon dioxide. This is why this molecular formula or formula of the silicon dioxide is SiO2, because each silicon is joined to 4 oxygen and each oxygen is joined with 2 silicons here. Okay, so let's continue. This silicon dioxide. So silicon dioxide, again, it is a giant covalent structure, as we said before, so it will have high melting and boiling points, like a diamond here. So diamond and graphite appear very different, but what they have in common, do not forget that diamond and graphite both are made of element carbon. So I will not erase the silicon oxide or dioxide for it, so I will show you the similarities between diamond and silicon dioxide here. Diamond and graphite, both of them are made of carbon atom. What does it mean? So it means that the simple atom or the raw material inside the diamond and graphite is carbon. But how they have different type of properties. It depends on, or answer is that this is about arrangement of atoms, carbon atoms in each structure. So if the question comes, why, as you know, the diamond and graphite, they are both consistent or made of same element, carbon, but why they have different properties? Only answer which you have to give here is that both of in each structure there are different arrangement of carbon atoms, or carbon atoms are arranged differently in each structure. So different forms of the same elements, as you see it's written here, they are called allotropes, different forms of elements. We only have diamond and graphite? No. Other allotropes, for example, oxygen element. Oxygen has another allotrope which is called ozone. Phosphorus, for example, has white, red, and black phosphorus. Sulfur element has rhombic, they are just examples, monoclinic sulfur, and etc. So they are called allotropes. So we don't need for now. Then. Okay, let's continue here. As I said before, these allotropes of carbon have different properties because of the items are bound in different arrangements, which are different giant structures. So what this PowerPoint explains to us. For example, what will happen if the word, the simple pencil in the world was made of diamond? So it will be the most expensive pencil, but it will never wear out and it will never need any sharpening. But if you want to write with it, it will damage all surfaces. And oppositely, if you change or if you make jewelries not from the diamond, from the graphite, what will happen? As you see what's written here, it is anti-thief graphite jewelry, so no one will want to steal it, and it will be cheap, the cheapest jewelry in the world, so it may stay in the clothes. As you know that graphite is very brittle, so what makes it brittle, we will talk about it. Okay, so it was about giant covalent structures. So let me explain the diamond to you. If you will go through the, let's say, this jewelry to the structure of in the diamond, what you will observe in the diamond, as we said, and as we showed in the silicon peroxide or silicon dioxide, as how the one silicon joins with 4 oxygens, in the diamond, 1 carbon will join with 4 carbons. So the arrangement of carbons here are called, or this shape is called tetrahedral shape. So see you in the next lesson. Tetrahedral shape. Now we will talk about in the other lesson. See you.